Hello and welcome to lesson 15. Today we are looking at the quotient rule, which is another one of our derivative rules. And of course, today's learning goal is to be able to differentiate rational functions using the quotient rule. And keep in mind here, now we have rational functions, and the quotient rule is going to be very helpful for that. So, previously in our last class where we saw the product rule, we actually worked on rewriting rational functions as a product with a negative exponent, and we were able to use the product rule. But now we're going to see that they actually have their own rule that we can use, and it'll help us to find the derivative. So if we have a function h of x, which is given by f of x over g of x, then the derivative of h of x, so h prime of x, is given by, and look over here, this should remind you of the product rule, except we have a subtraction here. So we're taking the derivative of f of x times g of x, now subtract from f of x times the derivative of g of x. And we now have this denominator here, which is new. So these two are different now, which is g of x squared. And g of x was just our denominator there, and that's why it's the denominator here as well, and now it's squared. And we have a requirement that g of x is not equal to 0, because if it is, then that would be an indeterminate case, so it's not defined. Now, in Leibniz notation, we have, if we have u over v, a function u over v, then the quotient rule tells us that we find the derivative of u with respect to x times v, take away u times the derivative of v with respect to d of x, and then in our denominator, we just have the denominator squared. Okay, now the proof of this, so consider h of x is f of x over g of x. Now I'm going to multiply by g of x and rewrite this as f of x. So f of x is h of x times g of x, and using the product rule, we have h prime of x times g of x plus h of x times g prime of x is equal to f prime of x. And we were actually looking for h prime of x, which is the derivative of h. And that's because our original function was h of x. So now it's just a matter of rearranging, right? So this is my term with h prime of x. So I'm going to move this over, and I'm left with f prime of x minus h of x and times g prime of x. And because I have that multiply by g of x, I'm going to divide by g of x. And now this itself, h of x, was f of x over g of x, because we don't want any h of x on this side. So we're just rewriting everything now in terms of f and g. So then I'm just rearranging here. I'll find a common denominator here, and then the g of x will go in my denominator, and I will be left with this expression here, which is my quotient rule as I want it. So yes, exactly right here. As I mentioned, in the lesson for product rule, we did see how to differentiate rational function by giving them a negative exponent, but now quotient rule is giving us another way to differentiate rational functions. So let's look at our first example here, where we're asked to find the derivative of h of x is equal to 3x minus 4 over x squared plus 5. So h of x being f of x over g of x, then we have f of x is 3x minus 4, and in my denominator, I have g of x is x squared plus 5. So now we're going to apply the quotient rule. So starting with my numerator, and I actually did the step here, but I'll show you. F prime of x is 3, right? Because 4 is a constant, and then 3x is just 3. And then g prime of x, or the derivative of g, is 2x. And that's exactly what we see here. So this is the 2x. And then here we have the 3x minus 4 and its derivative, which is 3. And in my denominator, I have the g of x squared. So x squared plus 5 is now just squared. And now I'm just expanding here for my numerator. So I will end up with 3x squared plus 15 minus 6x squared plus 8x. And this is just coming from here. And don't forget this when you're distributing or expanding this, you get 6 x squared minus 8x, but you had that negative in there as well. So you have to account for the negative there. And now simplifying, we're left with this expression right here. And that's all we had to do. Now, just another practice for you, try to use the quotient rule to show that the derivative of this function f of x is equal to this expression right here. One more thing I might do here for you is I'm going to show this example with the example we just finished with our product rule. So here, consider h of x is 3x minus 4 and x squared plus 5 negative 1. Then h prime of x is going to be 3x or so this is the derivative of f of x over or times g of x, but g of x, because it has that negative exponent, I just wrote it as a denominator. And this is plus, now I'm keeping 3x minus 4. And then we have the exponent of x squared minus x squared plus 5. And then we have x squared plus 5 squared. Again, this would have been x squared plus 5 negative 1, which is negative 2, and then the negative makes it go in our denominator. And finally, the power of function rule tells me that we need to find the derivative of the inside function, so 2x. And now, finding a common denominator, which is going to be x squared plus 5 squared, I'm going to have 3x squared plus 5. And for my second bracket, I'll have negative 6x squared plus 8x. And you can already see this is now this term here, or this expression there. And again, if I simplify this, I'll end up with the h of x, h prime of x that I was looking for, so the derivative will be the same, regardless of if you use power rule or quotient rule. It's just two different approaches, but generally what I find helpful for me, for example, is that the product rule applies for both. So I always learned just the product rule and then applied it for both. But again, it's good to have knowledge of the quotient rule as well. And we'll see in this lesson a few other examples, and hopefully it will make a little bit more sense. So our second example, we have the function y equals 2x over x squared plus 1, and you're asked to find the equation of the tangent line when x is equal to 0. So here, I'm going to start by finding my derivative function using the quotient rule. So now in Leibniz notation, we have dy by dx, and here, if this is f of x, and this is g of x, then we also have f prime of x is 2, and g prime of x is 2x. And so that's exactly what I'm seeing here. So this is my, and it's the second part a little funny because you have the two x's, but one of them is f of x and one of them is g prime of x, but they end up both being 2x. And now if we simplify this, I have 2x squared plus 2 minus 4x squared. And again, because you're finding the slope at a specific point, I don't need to simplify this any further. And I mean, it's already like pretty simplified. So for this one, I guess you can just write it as negative 2x squared plus 2. But when you come across big, more complex functions and you have a very complex equation here or an expression here, then you can just start by substituting that x is equal to 0, which is what I did here, and I was left with 2. And again, make sure that this is defined. So in our denominator, this is defined because it's 0 plus 1, so we're just left with the 1. So the slope of the tangent at x is equal to 0 is 2. And we also know that based on this function, again, same with substitution, my denominator is defined at x is 0, and then my numerator is just 0, so then the point is actually 0, 0. And so using y equals mx plus b, I can find easily that b is equal to 0. And so the equation of my tangent line is just y equals 2x. In the next example, we're asked to determine the coordinates of the point of this function where the tangent is horizontal. So let's interpret this first, what it even means. So for the tangent to be horizontal, we first need to be finding the derivative function, which is going to give us the slope of the tangent. And when the tangent is horizontal, it equals to a specific um, uh, it's going to be a horizontal line, which means that the slope is actually 0. So in other words, it's asking us to find x such that f of x is equal to 0. So that the slope of the tangent is is equal to 0. So first, we're going to use the quotient function to find the derivative the quotient rule to find the derivative function. So f prime of x is going to be given by, and let's do a little bit of interpretation here. So let p of x be 2x plus 8, and then p prime of x is just 2, and q of x is square root of x, and this has a derivative. And again, keep in mind this is just x to the power of half. So then we are left by power rule, half, and then x half, which is 1 over 2 squared of x. Okay, and so those are what I'm going to be using over here. And so this is my 2, this is my 2x plus 8, and this is just q of x and q of x there. And again, this is the negative 0.5 is just negative half, and that's what we are seeing over here. And light error there, that should be 2 squared of x. Okay. And now our denominator, which was squared of x squared, is just x. Now I can actually, because I have a difference here with just the denominator x, I can separate these into two terms. So I'm going to use what I know about square roots, and this is my numerator, or maybe let me write numerator, and I want to simplify that, and this is my denominator of uh, the x. Now, this part, I'm just finding, so the 2 there, I factored out 2 from 2x plus 8, so those 2's are gone, and I'm left with x plus 4. And it had a square root of x as the denominator, so I want to find a common denominator, so this term here is now 2x over square root of x. And now my numerator, I have 2x minus x minus 4. Keep in mind, this negative is for both of these, so there's like, think of it as a bracket there. But if you write it as such, we know the negative is for this whole fraction, so the negative has to be distributed. And Then you will be left with x minus 4 over square root of x, and then I bring back that denominator here now, and I have the x there. And now, uh, the tangent is horizontal when this derivative is equal to 0. And we can see that since this is a rational expression, this will only equal to 0 when our numerator is equal to 0. So when x is 4, then x minus 4 is 0. And we can see we have to check the denominator here as well. So we'll have 4 times 2, which is 8. So it'll work. It's defined. And so the coordinates of the point are going to be, and if you now use just f of x here, so f of 4, you get 4, 8. And the reason we had to do that was because it said the coordinates of the points of the function. So we had to find the coordinates, and that's our coordinates right there. And that's the end of our lesson for the quotient rule. So please make sure you're getting a lot of practice with this, especially for this lesson. I highly recommend practicing a lot of the product rule and the quotient rule like together. So try to find both answers using both methods and try to compare it to see that you get the same answer. And here are now your updated rules of differentiability. We have our power rule, sum and difference rule, our product rule, and the power of function rule. And now I've added the quotient rule in there for you as well with both notations. And for this lesson, you have some practice problems here, and as always, check Google Classroom for any additional material that you have to complete. And don't hesitate to reach out if you have any questions, and I'll see you all next class.